Now we talk about a logistic differential equation. In previous section, we already consider if the growth is when it is directly proportional to itself. For example, dn dt equal to a constant times n. We call this one exponential growth. Another one, if the growth rate is talked about, it is proportional to the difference between the number and the equilibrium value. The difference between the number and the equilibrium value. For example, p minus n. This one you call it bound growth. The exponential growth model can be only appropriate for a short time. But in the real world, because exponential growth, the shape like this one, will extend and there is no limit. But in the real world, impossible. The model implies the population always should be has a limit. Therefore, we combine these two models and we design another model. We call it the logistic differential equation. This equation can be rewrite become dn dt equal to k times n 1 minus n over k. I use ROK. I use a different symbol. I use K here, P here. The K here, we call it growth rate. And the P here, or you can say growth parameter. And the P here, we call it carrying capacity. Equilibrium, or ultimate maxima. And in here, the n will be bigger than 0, smaller than p. In a exponential growth, the graph like this. Right? In the bound growth the graph like this. You have an equilibrium, right? Or close to asymptote. But for the logistic differential equation, the graph will be like that. P here, this asymptote, or carrying capacity, equilibrium, ultimate maxima, they are the same thing. You have half exponential and then half bound growth. So you will find out for the characteristic of the logistic differential equation is when here is t, here is n, when t close to unlimited, n will close to carrying capacity. And if we do the second derivative, now I make the equation to second derivative. Take out here. dn dt equal to k times n minus kn squared over p, right? So second derivative d square n dt square, we can make here become p k n p minus k n squared kpn, because n is variable. kpn minus kn squared. So second derivative will be kp over p minus 2kn, and then do the dn dt because chain rule. And when second derivative equals 0, because dn dt is the rate, it must be bigger than 0. So only here equals 0. So we will get kp minus 2 here, 2kn. kp minus 2 kn equal to 0. Therefore, 2n equal to p, n equal to p over 2. So, this concept tells us the maxima rate of increase happen occurs when n equal to carrying capacity over 2. So you mean in the inflection point here.